Okay, we're going to continue talking about classification. So last time we talked about generative methods for classification. This was based on the Bayes rule for classification. And basically the idea is that we know exactly how we would classify if we knew the joint distribution of X and Y. And so if one possible way to do it is just to estimate this joint distribution through density estimation. Now we're going to take a very different approach using discriminative methods, and these tend to outperform generative methods, although that's not exclusively true. But they have a tendency to outperform generative methods. So, and the narrative for discriminative methods are very different, and it's a different philosophy, a different perspective on binary classification, thinking about margin-based methods and so on, which is fundamental to understanding modern machine learning, is to think about discriminative methods for linear classifiers. Primarily, we'll talk about linear classifiers here. Okay, so let's recall binary classification. We're just trying to predict a Y which can take two values. So I'm going to re-encode, just for convenience sake, I'm going to re-encode Y as a -1 and a 1. For example, elements of statistical learning, they tend to encode it as a 0 and a 1. That's probably more standard, but it's notationally a lot nicer to do -1, 1. This actually has more precedence in the machine learning community. It's sort of just a more convenient notation. So first of all, I'd like to mention that we could always just train a regression. We could forget about Y being binary. So just ignore the fact that Y is binary to begin with. Just train a regression as if Y took in continuous values. You can imagine what linear regression would do in this context. You would have -1 and 1 are your response variables, and your square error loss would be what loss you would use to train your regression, for example, in ordinary least squares. So we're going to come back to this, so it's important to think about this. But I would like you to step back and think a little bit about why it might not be a good idea to just take regression and to use regression for binary classification. Of course, the output for a regression is continuous, right? There's nothing that's forcing it to be binary. But you can, of course, just take the sign of f hat. This is one of the reasons why I like Y being encoded as -1 or 1, is that if you have a prediction, then you just check if the prediction is greater than 0 or less than 0. If it's less than 0, you predict a -1. If it's greater than 0, you predict a 1. And that's why Y hat being the sign of f hat of X is a reasonable prediction for regression. Well, we'll see why in a little bit, why you might not want to do this regression. But I'd like you to sit down and think about what regression does, and particularly what the square error loss means if it's used in the binary classification context. So linear discriminative classifiers are classifiers of the same type of form that we saw with LDA, where you have an output function, which is this f hat of X, and that's equal to this beta hat 0 plus beta hat transpose X. So I'll have this tendency to be a little fast and loose with the intercept. I'll often absorb into beta hat and make it so that X is in P plus 1, where X0 is equal to 1. And beta hat now is in RP plus 1. I'm going to try to tell you when I'm doing that. But typically, if you don't see the intercept, you can assume that it's just hidden and buried inside of the beta hat, and that beta hat is just RP plus 1, as we have a tendency to do. So this will predict. Our prediction is the same as before. We have f hat, as we just mentioned with regression, in the regression context, our f hat is our output. It's linear, and we'll just take the sign of it, and that's going to be our prediction for y hat. And typically, now we can think about what you would do if you, now the question is, how do we fit beta hat and beta not hat? And you could also think about k-nearest neighbors with even k. Like for example, 10 nearest neighbors. It could be you could set f hat to be the average number of nearest neighbors that have y being a 1, for example. But then you could very easily have a tie if k is even. But in that case, you could imagine flipping a coin in the case of a tiebreaker. So you can imagine situations where this f hat is actually equal to 0, and instead of biasing it towards 1 in the way that we do it here, you flip a coin. You just generate a Bernoulli random variable to determine whether it's predicted a 1 or a -1. So those are sort of caveats to this. But instead of k-nearest neighbors, we're going to focus on binary classification in this lecture, for the most, or linear classifiers in this lecture. So the loss function here, it measures the success of our predict function. So let's just recall that our loss function here, for binary classification, we're going to tend to think of it as the 0-1 loss. So this is very different from the square error loss in a lot of ways. But the basic idea is if I'm predicting y hat to be 1 or -1, then we just see if yi matches that 1 or -1. And then I incur a loss if I'm wrong, and I don't incur a loss if I'm right. Right? So this is a big difference between classification and regression, is we're really measuring how many times are we wrong or right. And in this loss, we're equally weighting the different types of errors. So if I predict a 1 and it actually is a -1, or if I predict a -1 and it's actually a 1, those have the same loss, and we're just going to call that loss 1, for example. So this is the 0-1 loss. And then our test error is just going to be the misclassification rate. So if we use this loss and then we look at our test error in this loss, that's the number of times we were wrong in our classifier. So if we do care about this loss, if we just use the empirical risk minimization framework like we did before, then you will want to minimize our training error with the 0-1 training loss. But then if you think about what this optimization program is, it's the following thing. You're going to, and this is for linear classifiers. So we have a beta transpose xi, and I've absorbed the intercept into the beta now. And you're just checking what the sign is. That's what our prediction is. And now we're going to see if it's equal to yi or not. But if you think about this, this is a very discontinuous loss function. The expectation of this, or sorry, there's going to be a point at which you just change beta a little bit, and suddenly it'll go from being a 1 to a 0. This loss will go from being a 1 to a 0. And so this is going to be a discontinuous. This is going to be a discontinuous loss function. And so it's very hard to optimize. You can imagine, before we had talked about loss functions like the hinge loss, which are, or we will talk about. We've mentioned loss functions that are the hinge loss, and other regularizers in the lasso, like the absolute value or L1 penalty, and those were they were not differentiable, but they were convex, but they were still continuous, right? There weren't massive changes that could be in the function if you just made a tiny change in the parameters, the underlying parameters. You didn't have that situation. With this, you do. So it's very hard to optimize, and you can think of this more like a combinatorial optimization. So it's very hard to optimize this, and it's often an NP-hard problem. And you couldn't imagine doing something like first-order optimization. Even to adding insult to injury, this is also a non-convex loss, and so that's another thing, that issue that we run into. So let's imagine a simulation for illustration purposes where we have two classes, positive and negative, and we want to find a good classifier, a good linear classifier for these things. So the first question is, what do these classifiers look like? So I'm going to claim here, and we'll do it in an exercise, I'm going to claim here that these look like hyperplanes. So these are planes in your p-dimensional space, and on one side we're predicting that as a plus, and one side we're predicting it as a minus. If you think about what the 0, 1 loss does, if this side is predicted plus and this side is predicted minus, then it's the number of pluses on this side plus the number of minuses on this side. That's what and divided by the total number of points. That's what the 0, 1, the empirical risk is going to be for the 0, 1 loss. And there's a lot of different lines that we could imagine using, right? And as you change these lines a little bit, suddenly you're going to get big jumps you're going to get jumps in the 0, 1 loss because of that discontinuity that I mentioned before. And we really want to find a line that separates one side, does a good job of separating the pluses from the minuses with few misclassification errors. Logistic regression is going to turn out to be one of these ways of doing this. And then if we look at our losses, what the losses mean for these points after we have hypothesized a line. So this is for some fixed beta. Let's just look at the losses for one of these hypothesized hyperplanes. Then on one side, these are all the misclassifications on the positive side, and these are all the misclassifications on the negative side. These are weighted by the loss. So they're weighted by the loss as just 1 for 0, 1 loss. So we're going to think about this. How do we weight? How can we weight these points that are misclassified so that as we change our line here, we can get an empirical risk minimizer that is easy enough to solve, and also will give similar performance to the thing we want to do, which is minimizing the empirical risk for 0, 1 loss. Okay, so I'd like to point out before we move on, just like the lasso, this is another situation in which we want to solve something from a statistical perspective. We would like to solve something which is the empirical risk minimization with 0, 1 loss, but we can't do that because of computational reasons. So this is the second major instance in this class where we've come across a problem that is, there's a statistically optimal problem that we would like to solve, but computationally we can't solve it. And this is really where I think machine learning distinguishes itself as a field, is we have to make compromises between the statistical performance, what we want to do statistically, and between based on the computational complexity of the methods that we're using. Okay, so as an exercise, I want you just to show or convince yourself that a classifier, which is defined by y hat is equal to the sign of beta transpose xi, is defined by a separating hyperplane. And we can assume that there's an intercept absorbed into this by setting xi 0 equal to 1. And I'd like you to convince yourself that this classifier being a certain value actually is defined by a hyperplane. Particularly, y hat equal 1 is on one side of the hyperplane, and y hat equal -1 is on the other side of the hyperplane, and that's a defining feature of this prediction. And then what's the normal vector to this hyperplane? So go ahead and solve this problem, and we'll answer it when we return.